Okay, so again, this is the expression for the Doppler shift in the case for outward radial motion, theta equals 0. And at this point, we should recognize that the way we set up this um, little example, v, the velocity, the v is a speed, not a velocity. Okay, it basically just gives the speed. Theta gives the angle, and so the velocity or the speed v is always greater than or equal to 0, and of course less than or equal to c, the speed of light. And this just implies that beta is between 0 and 1. Okay, so if we look at this expression, then what we see is that the numerator is always going to be less than or equal to 1. Okay, if beta is anything greater than 0, then the numerator will always be less than 1, and the denominator will be greater than 1. And so this ratio is always going to be less than 1. Okay, and so 1 minus beta over 1 plus beta is always going to be less than 1, okay, if beta is greater than 0. And so what this means is that the observer sees a smaller frequency than what the source put out, and the sources than what occurs in the source's frame. Okay, now these, I have to be careful, these are Greek letter nu, these are frequencies. Okay, this is a velocity, beta has a velocity, these are frequencies. Okay, and so this we call a redshift. Why red? Well, if you think about the visible spectrum going from red all the way up through blue to violet, the red end of the spectrum is longer wavelengths, which means lower frequencies. The blue end of the spectrum is shorter wavelengths, which means higher frequencies. So when we have this shift to lower frequencies, the observer sees a lower frequency. That corresponds to longer wavelengths, which in a shorthand way of saying that is just gets shifted towards the red end of the spectrum, or redshift. So whenever we have a source moving away from an observer, we'll get a redshift. Okay, the second particular case we're going to consider is when theta equals pi. Okay, in that case, the velocity of the star, the velocity of the star is pointing directly at the Earth, so it's approaching the Earth directly. Okay, so we'll call that inward radial motion. Okay, so in that case, if you work through it, then theta equals pi, so cosine theta equals -1, and you get that the observed frequency is the source frequency times this factor, 1 square root of 1 plus beta over 1 minus beta. Now if you think about this again as we did before, this is always greater than 1 if beta is greater than 0. Okay, the numerator is always going to be greater than 1, the denominator is going to be less than 1. Okay, and so that means that the observer always sees a higher frequency than the natural frequency, the proper frequency at the source. Okay, and this is called a blue shift for the same reason that I explained the red shift. Okay, so whenever you have blue shift, that means that the source is approaching the observer. And the final special case we're going to consider is when theta equals pi over 2, so that the source is going perpendicular to the line separating the Earth and the star. Okay, so it's going transverse or tangential to that separation line. Okay, so in this case, theta equals pi over 2, so cosine theta equals 0. And if you do the math, you get that the observed frequency is equal to the source frequency times basically 1 over gamma. So it's 1 minus square root of 1 minus beta squared. Again, this is always going to be less than 1. Okay, and so again, the observed frequency is going to be less than source frequency in this case.